It's a great pleasure for me to introduce the next speaker, Dr. James Allan. And he received his PhD from the University of Manchester in 2004. And during his PhD, he developed the data analysis method for aerosol mass spectrometer. And he is currently a reader in the University of Manchester and also a research scientist in the National Center for Atmospheric Science in the UK. And he's also a senior editor for the aerosol theme at the Journal of Atmospheric Chemistry and Physics. He's specialized in the in-situ measurement of atmospheric aerosol with online instrumentation, including measurement of black carbon, and also studies the black carbon emission and properties based on lab work. So for today's talk, he will give us the topics related to black carbon and its optical properties and the mixing state based on the atmospheric measurements. Let's welcome Dr. James Allan.
Hi, thank you for that kind introduction, and also thanks for inviting me for this talk. What I'll be showing here will be, it's a culmination of work by a lot of different authors. So it's not just all my own work. I'll be giving a list of the contributors at the end of this talk, so please don't think I'm taking credit for everything. So what I'll be talking about, I'm going to start off with a quick introduction to the effect of black carbon and climate. I mean, it will be familiar to a lot of people here, I'm sure, but I think it's important to set out the motivations for how I'm certainly approaching this from a measurement perspective. I'm also going to be mentioning black carbon on air quality, going to be discussing the research challenges, what motivates us to study black carbon, and then I'll be talking about my actual research. So mainly focusing on the single particle subphotometer. We're going to be looking at black carbon in urban environments, going to be talking about measuring and modeling optical properties, and also finally measuring the black carbon mixing state. So I'm sure plenty of you have seen this figure before. There's a very comprehensive review led by Tammy Bond 9 years ago in JGR. For those that haven't seen it, I thoroughly recommend you check it out. But to recap the effects of black carbon on climate, we have various effects. It can absorb solar radiation, which using the old AR4 parlance would be called direct forcing. Scattering solar radiation, which again would be calling direct forcing, but this would be a cooling effect rather than a warming effect. Black carbon can contribute to CCN, more of that later, which would be a cooling effect through indirect forcing, but it can also prevent cloud formation through burn off or inhibiting convection. And finally, it can also cause warming by enhancing snowmelt. These are all very complex effects. The exact warming cooling effect depends on a lot of parameters like altitude, surface albedo, etc. And this is all further complicated by the fact that, as we all know, there are lots of other emissions that can counter effect the warming effect, such as SO2. But when we think about the effect on climate, the number that most people like to think of in terms of like a headline figure would be the radiative forcing in watts per square meter. You know, I've certainly used figures such as the ones I'm about to show in the introduction of many of my talks, because I'm sure many other people have. And one of the ones that created a lot of buzz a number of years ago was Ramanathan and Carmichael back in 2008. And they produced this estimate of the effects of black carbon on local and on regional and global climate, and came up with this overall top of atmosphere forcing of 0.9 watts per square meter. And this led, and I just cannot get this quote out of my head, back at the European Aerosol Conference, McGee Scientific announced black carbon to be the world's #2 greenhouse gas after CO2, which I'm hoping everyone appreciates. I'm hoping that's intentionally ironic, that statement. So going on to the Bond et al. Review, they estimated a total climate forcing of 1.1 watts per square meter, which is really quite large. So if you translate that onto the IPCC report, the fifth assessment report, which was done in the same year, black carbon had wasn't quite 1.1 watts per square meter on this graph, but you can it's still fairly large, this block here. It's kind of comparable to the direct effects of methane, which is actually quite huge. Well, then fast forward a while, onto the next IPCC report. Now, this is from Thornhill et al. 2021, which is the CMIP into comparison. And then all of a sudden, the numbers are looking a lot smaller. They produced a multi-model average of 0.15. And then onto last year's IPCC report, the black carbon contribution is all of a sudden looking a lot smaller. This is in terms of degrees Celsius warming rather than watts per square meter. So if we compare our two most extreme examples, the 2013 Bond et al. Review and then the 2021 CMIP 6 Thornhill et al. Into comparison, and it would appear at the face value that the radiative forcing has changed by nearly an order of magnitude in the space of only 8 years. So what happened? Why did it change so much? I mean, I think the first thing we've got to point out, and for those not familiar with how these climate models work, it's important to stress that we are not comparing like with like here. The most recent climate model into comparison exercise was using much more advanced coupled models. And this is quoting the effective radiative forcing, as opposed to the more kind of instantaneous radiative forcing of the earlier models. So this is including a lot more feedback processes. And the term that's often used in the recent literature for why the effective radiative forcing of black carbon is so low is rapid adjustments. Examples of these might include the effects on the dynamics and meteorology. So black carbon in the upper atmosphere will increase the atmosphere's stability, and this will increase the persistence of marine stratocumulus, which generally have quite a high cooling effect. And then it will also have effects in the upper atmosphere as well, such as thinning high altitude cirrus, which can cause a warming effect. So taken all together, these complex processes means the effect of black carbon on global climate isn't quite as big as what was thought 10 or so years ago. But does this mean that black carbon isn't important for climate? Definitely not. One of the big things to stress here, that in these rapid adjustments that are being talked about, in order to counteract the previous large estimates, these effects must be hugely significant. And that must mean they must be having a very profound effect on dynamics and meteorology in the atmosphere. So even if black carbon isn't the biggest contributor to global temperature rise on a global scale, it still must be having a very large effect on regional climate. Because remember, it's a very short-lived climate forcing agent. So, you know, you're only talking weeks at most. And then, so this could be having a big effect on rainfall patterns, monsoon, general circulation, etc. But one thing you must need to stress is that in order to predict these accurately, this is where you really do need the most advanced and up-to-date coupled climate models. So a recent example of this is a paper that's currently in review. Well, this is looking at the wildfire season in the austral summer of 2019 to 2020. There were some very large fires in Australia. So this is some of the largest, most significant fire season on record. And it's been noticed that this caused an uptick in stratospheric temperature. And some collaborators I have at the University of Exeter have been modelling this. This uptick here is the biggest seen since the Pinatubo eruption. And what's been seen is that you can't, this anomaly here can only really be explained by modelling the biomass burning aerosol, but also coupling it to how it affects the lower stratospheric ozone as well. And they reckon that on top of this, it's also having a big knock-on effect on the polar vortex, which means the Antarctic ozone hole is persisting for longer. But let's not forget that black carbon is also a component of air quality. There's indications that for short-term exposure at least, it has a higher gram for gram association with health effects than PM2.5. Although it also presents this interesting problem in that we don't think that black carbon itself is possibly the toxic agent. You know, it may be a proxy for other co-emitted toxins. So, you know, things like PAHs, nitro PAHs and so on. So we're very interested in it from that perspective as well. And so I think, you know, after that introduction, I think it's important to kind of take stock and think of why we're making the measurements that we do. In the spirit of this special symposium, we've got to ask these questions, you know, what can we look towards in the future with the climate change for mitigation and adaptation and so on. I mean, one of the questions is in the context of the Australian case study, we can expect wildfires to increase as the world warms, as areas become more arid and hotter, more susceptible to drought. Will fossil fuels emissions decrease? You know, so as we begin to phase out fossil fuel burning, or at least mitigate, make the fossil fuel applications a lot cleaner, can we expect those emissions to go down? We're expecting a lot of countries to undergo economic development over the coming decades. Can we expect the emissions of black carbon to increase correspondingly, or would we expect them to go down as they adopt cleaner technology and better farming practices? And finally, we're also looking to new sources of energy. So biomass in particular, will this emit more or less than the fossil fuel counterparts? Now, this is a very big issue in the UK right now, and also in other countries in Europe, because burning wood for domestic heating has become a lot more popular in recent years. And so there's a lot of air quality considerations there. Now, most of the work I'll be showing you is using this instrument, the single particle subphotometer. This has been around for a while now, manufactured by Droplet Measurement Technologies in America. This is using the principle of laser-induced incandescence to measure the black carbon content of individual particles, but it can also size particles by looking at the scattered light. Now, what this does is it passes particles through a high finesse, high intensity laser cavity with a neodymium YAG laser, and this destructively heats the particles and measures the black carbon content using by inspecting the black body function as they glow. And this is an example of the type of work that we've done with this. So this is comparing London with Beijing and with Delhi. This is showing on the x-axis here, looking at the leftmost graph. This is showing black carbon histogram versus the core size. So the size of the black carbon that's present in individual particles. But on the y-axis, we have the amount of light that it scatters. And you notice that we've got two populations of particles in London. One population with these small cores that don't scatter much. They only scatter about as much light as we'd expect for a bare black carbon particle. And then compare that to ones which scatter a lot more. That means they're coated with something. That there's some more matter that present with the black carbon. And in London, we associated these more thickly coated particles with wood burning. But in Beijing and Delhi, we saw some more complex mixing states there, and which we're able to associate with some sources to a greater or lesser degree. Another advantage of the SP2 is a very fast measurement, and we're able to do eddy covariance measurements with this. If you can make measurements on top of a tall tower. Again, we've managed to do this in Beijing, Delhi and London, where we've managed to find suitable structures. And we've got some of this published. And this is a very good way of looking at the emissions from a city directly. We can use this to validate emissions inventories. And we've generally found that the local emissions inventories, because the inventories are generally optimized for much larger scale emissions, we've still got work to do to downscale these for kind of city scale environments, but we're making progress. And a slight variation on this is the SP AMS, the subparticle AMS. I'm not going to talk about the AMS in detail. It's a very well-established instrument by now. But this is a variation on it, where instead of vaporizing particles using a heated tungsten surface, we vaporize them using an SP2 laser. Now, this means you can look at the mass spectral composition of black carbon and its coatings. It doesn't give you the incandescent signal, but what it can do is look at different black carbon types by composition. And if you've got the mass spectrum, then you can apply PMF to it, factorization, which is something we use very commonly in the AMS community for looking at different sources. And this is a case study we published last year where we were able to look at different sources according to the mass spectral composition. It's also worth noting that we're able to see fullerenes in the mass spectral signatures as well. That's not to say that the soot itself contains fullerenes. It could be being formed during the vaporization process, but it means we are able to use it to distinguish black carbon types. And this paper last year, we were able to separate out 5 different signatures for black carbon, which we're quite excited about. But then a lot of these results I've shown are very interesting from an air quality perspective. But if we want to know the effect of black carbon on climate, we need to be looking at the atmosphere on much larger scales. So a lot of the results I'll be showing now, these were taken on board the FAM BAE 146. For those not familiar, this is the UK's main atmospheric research aircraft. It's been in service for a good while now, since 2004. It's recently had a midlife upgrade approved, so we'll get a lot more use out of it in the future. It's a very versatile multi-role aircraft, and it's also, in terms of payload, it's also Europe's biggest atmospheric research aircraft. And one of the instruments, of course, that we regularly like to fly on it is the SP2 here, which is a picture of me posing in front of it. And we've collected SP2 data in a lot of different environments around the world. And an example of the type of work we've done, this is from some flying we did in the Arctic region. This is a paper that Dantong Lu did a while ago. And what we're able to do is, when we intercepted individual tropospheric plumes in the Arctic, using FlexPath back trajectory analysis, we're able to try and assign source regions for these, and then try to estimate what kind of history the air mass had in getting this black carbon up to the Arctic, where it might conceivably perturb the climate. And one of the things that I personally don't think gets enough attention when people are studying black carbon properties and processes is the properties that might affect scavenging. Scavenging is important because this is the main loss mechanism for black carbon in the atmosphere. So it takes black carbon's lifetime. But certainly when black carbon is being transported long distances in the troposphere, it frequently has to pass through a cloud. And that cloud might be precipitating, and it might remove the majority of the aerosols as it does so. However, if the black carbon does not get incorporated into cloud particles, so if it's too small or too hydrophobic, then it might be able to pass straight through the cloud, be uplifted into the free troposphere, and then from there it might persist for a very long time in the atmosphere and cause the various climate perturbations. But not all black carbon particles will be removed. As I said, the larger ones, they're more likely to be activated. The ones that come with a coating, the ones that are more hydrophilic, those ones might just simply get removed, and so they might not participate in the subsequent processes as much. So it's something we really have to pay attention to, and it's something we do have observations of occurring in the atmosphere. So this is a paper by Johnny Taylor a few years ago, looking at comparing some plume interceptions for some Canadian biomass burning plumes. And using the SP2, we're able to compare 3 different plumes 2 of which were direct plumes from the fires, and 1 of which had passed through a precipitating cloud, which was plume 3 on these graphs. And one of the things we're able to show is that indeed, plume 3, we still had black carbon in it, but these black carbon particles were smaller, they were more thinly coated. These are the ones that weren't removed by scavenging, and so these are the ones that could potentially persist in the atmosphere for longer. And so if we know these processes are going on, we want to be able to model them, so we can determine what their effects are. So the effects of coatings, these can increase the mass absorption cross-section and the single scattering albedo of particles, so perturbing their optical effects. This has been something that's been long studied, and also the CCN potential, which in turn will affect its cloud impact and scavenging potential. So if we want to know the effects of black carbon climate, we want to be able to predict these, so we want to be able to measure them from the perspective of an observational scientist. Now, modeling the optical properties, as I'm sure many people are aware, gets very complicated. There's a variety of different models that can be used. One of the most common ones for modeling spherical particles is using a simple Me-based model. So we can model the individual particles of organic matter and black carbon, say, but as we all know, and as we've shown with our data, that the black carbon and the coatings are frequently mixed, and then the model predictions will change depending on how you treat them, how you treat the mixture. You know, so for instance, you can use Me to model concentric spheres, or you can just invoke some assumption about the overall refractive index of the particle based on the respective volumes of the 2 components. So you can use a simple volume mixing relationship, or you can use an effective medium rule, or you can even start to play some games with assuming that these particles are aggregates, and then start to invoke some rules there about how they might interact with each other. But all of these are approximations. If you want to go more complicated models exist, such as the multi-sphere T-matrix model. And then if you want to get really complicated, you have the very explicit but very complex models, such as the discrete dipole approximation. One of the things that we've shown, this is a paper that Dan Tong Lu led in Nature Geosciences a few years back, was when we were trying to study these particles in the laboratory. This was using a diesel engine to generate black carbon, but running it under different conditions, and also comparing it with ambient particles. Is that we showed that when you're using various Me models, different treatments apply according to different coating thicknesses. So it seems that we need to, the particle needs to get a certain amount of coating before a mixing rule like the core shell model or Maxwell or an effective medium would apply. And we think this is because the coating is not fully enveloping the core, and it doesn't give the absorption and scattering enhancements that you'd expect with the kind of a more uniform coating. And this was later replicated the following year in another paper using a T-matrix model. But when we want to get out into the atmosphere, we want to measure these things explicitly. This instrument here is one we've compared to a lot, which is the Excalibur rack used on the BA-146. This was built by the UK Met Office and uses multiple photoacoustic and cavity ring down channels to measure absorption and extinction. And this is another paper that Johnny Taylor produced a couple of years ago. And this shows another kind of a similar thing, which is that when we're trying to use Me models, and bearing in mind that we can't constrain, I mean, this isn't a nice, comfortable lab environment anymore. If we take the SP2 data and try to compare with the absorption and extinction data, we can't seem to replicate it uniformly using a single model. And in this particular case is looking at fire plumes off West Africa. So what do we do? You know, doesn't appear that a single me-based approach will work, but at the same time, the kind of data that's carried by climate models isn't really suitable for constraining more complex models of optical properties. So what we need to do is just try and find a modeling treatment that does a good enough job that is suitable for use in climate models, etc. And so what we're trying to do from an observational perspective is determine things like the refractive index. This is the complex refractive index, so real and imaginary parts. And we're also trying to model a mixing model that does a good enough job that we can trust it for climate modeling. So when we do experiments in the lab, I couldn't resist showing this paper. So this is one led by the session by my moderator, Danny Ting. This was some work we did in Leeds on African cook stoves and domestic heating stoves, which is all very well for studying specific appliances. Well, as is shown in this paper, we get to these very highly complex mixing states where some black carbon is mixed with organic carbon, some isn't, and trying to use that to constrain any kind of modeling, optical model is difficult. So instead, we've got this alternative approach. We've published 2 papers on this now, where we burn very small samples of wood in a more controlled combustion condition, where you have, if the wood sample is completely enveloped in a single flame, then it will only ever emit either black carbon on its own or organic matter on its own, depending on whether it is pyrolyzing before it ignites or whether it is a smoldering. So using this approach, we can study wood burning black carbon or organic carbon on its own. But then we also need to constrain the size of these particles. That's because the scattering in particular is massively sensitive to the size of the particles. So if we're going to apply an optical model to it, we need to be able to supply particles of one fixed size. Now, the conventional method is using a differential mobility analyzer, but the problem with these is you have multiple charged particles, and these can confound the measurement because they're much larger than the particle size of interest and have a very nonlinear effect. One that's we've used a few occasions is the centrifugal particle mass analyzer produced by combustion. This again suffers from the problem of multiply charged particles, but it has a nice advantage in that it selects particles according to mass. So that's a good way of constraining the properties like the mass absorption coefficient. Well, then finally, one which has been a real game changer has been the aerodynamic aerosol classifier, which is another instrument by combustion. This one sizes particles centrifugally, but using the aerodynamic diameter without any charging. This one doesn't have any multiple charging effects. So this one is highly suitable for constraining optical effects. And so what we've done is use this in a series of experiments in Exeter and Manchester, where we've connecting all these sizing instruments and various other instruments looking at the black carbon composition and properties in various different configurations. We've connected this to the emissions from the controlled wood burning experiments that I was talking about. Inverted flame burner, that some Canadian group brought over. An aerosol atomizer doing black carbon proxies, a diesel engine, and we've also got a photochemical chamber where we try to make secondary organic aerosol, which can also which can also be light absorbing in its own right through so-called brown carbon. And then depending on the experiment we were performing, we have multiple different instrument configurations. This is in a paper that Dawei Hu published last year, and if you're interested, I recommend you check it out. And what we're able to do with this is constrain the size and the optical properties of the individual particles, and then for the pure component particles I've shown here, derive their refractive indices, which can then be used in optical models. We're still working on the data concerning the mixing state models, so watch this space for that one. But we're able to show that we're able to derive the refractive indices of things like black carbon. We're able to show that secondary organic aerosol from alpha pining is non-absorbing, but we're able to observe that secondary organic aerosol from cresol does have a kind of a brown component. And then finally, another thing you can do with these sizing measurements is also look at the mixing state of atmospheric aerosols. This is highly important when you're determining not just the optical properties, but also the cloud forming potential and scavenging efficiency of the particles. One of the things that we did fairly early on, nearly 10 years ago now, was published nearly 10 years ago as a paper by Dan-Tong Liu looking at the composition and black carbon content of particles by hygroscopicity at a remote site in the UK, showing that you have this atmospheric processing of black carbon to make these particles larger and more hygroscopic. But this was using a HDDMA, which had a very long scan time. More recently, what we've been able to do is, this is a paper by Shenjie Yu, published a couple of years ago. This is from Beijing, looking at a CPMA and SP2 in series. So this is looking at the black carbon mass fraction of particles and able to produce a 2D histogram showing this mass fraction as a function of the overall particle mass. This is using an inversion algorithm produced by Jason Alford's group in Canada. And what we're able to do then is then convert this to a mixing state index parameter as used in other publications, and also the particle resolving models like PART-MC. And this is able to show that the mixing state in Beijing is highly complex, and some of the behaviors changing depending on summer and winter. Now that opens some interesting possibilities about how these plumes behave and how we might expect their cloud interactions to behave downwind. And then, of course, more recent than this, we've also done some follow-up measurements. This is in collaboration with Dan-Tong Liu, looking at the particles selected by the aerodynamic aerosol classifier. So what I mentioned earlier, this has an added advantage of having a higher throughput as well. So we're not just looking at the SP2, but also able to make measurements with an AMS, a CPC, and a CCN. So we're measuring composition and the CCN properties of the particles. And we're able to do this as a function of aerodynamic diameter. And this was able to capture some interesting results, such as showing that we have these black carbon particles, but they seem to, this is a Beijing suburb, Pinggu, where there's some, we think, more dirtier sources of black carbon, and that these tend to occupy the larger particles rather than the smaller ones. So to summarize, black carbon is very highly important for meteorology and climate, but we do have to bear in mind that we need very complex and coupled models to really properly evaluate their effects. And we also need to study these very complex processes on a detailed level. So the single particle subphotometer has been a highly useful instrument for measuring black carbon in the atmosphere in the lab. We're making measurements in the ambient atmosphere in the lab of optical properties and CCN properties, and we produce some highly useful data looking at these, and but more work's needed to do to see how we can best reflect this in climate models and so on. And then also using the the SP2 and other instruments in series with a CPMA or AAC, that has allowed us to derive some very useful data on mixing state. So finally, I'd just like to give some acknowledgements. So most of what was funded, most of the work here was funded by NERC in the UK, although some other sources as well. And I would like to thank all these, all the following people as well. So talking not just people at Manchester, but also other collaborators as well outside. So thank you.
Thanks, Dr. Allan, for your impressive talk. So now we are open to question on site and online. Is there any question for? Okay.
Hi James. This is Casey Shell from National Taiwan University, and hope you still remember me. We attend the IRA meeting together, right? Take care of the website for a long time. Thanks for the contribution. So my question is more technically. First one is I saw one of your slides use simultaneity for part of your experiment. Well, that simultaneity process changed the mixing state, and how do you resolve that problem, or how do you consider that process? Because you're talking about the morphology or the mixing state, I think that is quite important. So that is one thing. And for the mass classification, yeah, it's cool. Combustion is also responsible for this Asian Universal Conference. It is also called AAC. I think that is also why they sponsor the conference. But anyway, so I would like to have one, but not that rich to have one. So I have an APM so far. So you comment the performance of between these instruments like APM made by Candlemax and also the AAC by combustion. And I think there is a limitation, the detection limit for AAC, because it's solely based on the aerodynamics, right? I saw your data like down to like 100 nanometers. Yeah, it's pretty cool. Surprised me. Based on aerodynamics, you can go down to like 100 nanometers. I surprised. The following question is like, well, diffusion cause any problem for your measurement at this size? And also, most of the black carbon particle actually reside on the particle size less than 100 nanometer, right? So that is my question. Thanks.
Thank you. No, those are all very excellent questions, and I would have covered some of the detail had I had more time. The thermal denuder one in particular is something that I do feel quite strongly about, because there is a lot of work that's been previously published, and also we've done stuff with thermal denuders as well, which is like looking as a means of removing coatings, the non-black carbon material. And yes, that can work great, except I have my strong suspicions that thermal denuders are not good when we're studying biomass burning aerosols in particular, because we know that there is refractory organic material within biomass burning emissions that will char before it vaporizes. That's part of the reason that motivated me to do these experiments where we're not producing organic matter and black carbon at the same time, because I don't trust the thermal denuder not to perturb the particles. The effect on morphology is even more interesting. We do have some data in that on Dawei, whose paper last year, where we are able to show that we can do restructuring with the particles, but it's not just the heating. We think it's also to do with interactions with an aqueous coating as well, so disrupting the forces between the black carbon spherules. But yes, your point's very valid, and that's why I try not to use thermal denuders too much. Regarding the APM, I wouldn't draw an equivalence between the APM and the AAC, because the APM selects by mass, the AAC selects aerodynamically. The closer equivalent to the APM would be the CPMA. Now, there's some technical differences in there that I'm sure combustion will say makes their product better. I'm not going to get involved in that, but I suggest you take that one up with Jason Alford or someone. But fundamentally, the APM and the CPMA are producing very equivalent data, and I've seen similar experiments done between the APM SP2 as the same as the CPMA SP2. They're very analogous, and I think metrologically they produce the same kind of thing. As regards the detection limit of the AAC, well spotted. That was a problem for the work that we were doing here. The problem was not the AAC though. The problem was that for the smaller particles, because we were making mass-based measurements, the signal to noise ratio of the much smaller sizes was meant that for when we're doing ambient monitoring, the signal to noise ratio, the AMS in particular, went very low. The SP2 can also not detect black carbon particles below about 70 odd nanometers. So the limitation there was not with the AAC, but with the SP2 and the AMS. I think that was all the questions.
Yeah, I think that is most of the questions. I just curious what do you think like the diffusion will be a problem for your measurement in
yes, yes, sorry, I've forgotten about that one. Yes, diffusion is a major problem when you're studying the smaller particles. One of the, particularly when we're studying when we're studying these particle properties, though, the way that we try to design the experiment is when we're making simultaneous measurements, is that when we're looking at the intensive properties, we can normalize the signal to something like a CPC. And if we are confident that we've got a similar amount of tubing leading up to the individual instruments, then any diffusion losses will hopefully drop out of the equation. Obviously, that doesn't help you if you lose all of the particles, though. So this is going to be an issue for the very small particles, certainly. Okay, great.
And one more thing, so the last one is, yeah, because the detection limit is 100 so far is based on the data you show, but like black carbon we always think about it is on the peak probably 50 nanometers that is out of your sight, right? How do you resolve that, or do you have any comment on that one, or what do you think?
Yeah, I mean that's a very good point. Yes, there is a fundamental detection limit on the SP2, which is about, I'm going to say 70 nanometers for the black carbon core. And you are absolutely correct that we do have to worry about black carbon particles that are smaller than this in the atmosphere. Aviation emissions is one of the big ones. When we have these very small particles, the SP2 will not detect those at all. So yeah, I mean, that presents a big problem. Certainly the bulk absorption instruments, so your photoacoustic spectrometers, they will still detect the absorption there. So if there are these plumes that the SP2, they are these particles that the SP2 is not detecting, then we can still pick them up using an absorption measurement. So photoacoustic or even a filter-based one. But yeah, it would be very nice to be able to look at the smaller ones using a different instrument. You can measure them with the bulk laser-induced incandescence instruments. However, I'm most familiar with those being used for emission measurements rather than ambient measurements, though. So that does present a technical challenge, yes.
Okay, I think I asked another question. I'll let the others to ask a question. Okay, thanks, Alan.
So I think this question on or type. Please.
I am JP Chen, previous speaker. Thanks for the interesting and technical work. I have two questions. One is I'm wondering how you define the mixing state index. How is it calculated? And second is when you calculate the mixing state index, which measurement data are you using? I saw the DNA on the slide you mentioned, but does it also involve SP2? Thank you.
Yeah, it's a very good question, that, because the mixing state index that we use, it's using the same formulation that was developed by Nicole Reamer's group, Urbana, using the Part MC model. But however, it's still not exactly the same as the mixing state index that's been published in other papers, because what we're making this measurement with is the CPMA and the SP2. so the sp2 downstream of the CPMA. And what we're defining the mixing state as is comparing the particle, how the black carbon is distributed amongst the particles compared to all of the non-black carbon components. So we're getting a fundamental different measure compared to, say, these other papers that have produced a mixing state index from, say, the SP AMS, which is measuring other things other than just non-black carbon. You know, that's able to speciate the coating materials. So I don't want to get roped into the technical details of it because it does get really technical. But I would the paper was about Shenji Yu. I recommend you check it out if you want the technical details. I have to credit him with doing the actual calculations, though. This was something to his credit he came up with off his own bat. So I suggest you take that, have a look at his paper on that.
Okay, thank you. I've got a quick follow-up question. So you're not distinguishing between internal mixing and external mixing, is that right? Yes,
that is correct. So you've got like a mixing, you've got like a scale, like, you know, 0 to 1, where you're comparing a completely externally mixed population versus a completely internally mixed population.
Right. Any question? Please, you.
Hi, James. My name is Stephen Griffith. Thanks for the awesome talk. Mine is a non-technical question. Going back towards the beginning of your talk, you were comparing the most recent IPCC report to the Bond et al. Review, and basically that downplayed the importance of black carbon to positive radiative forcing. And I think you called it rapid adjustments that they applied to essentially make it almost a net zero effect or something like that. And I'm just wondering, the uncertainties I would have assumed may have grown in the radiative forcing estimation because of all those rapid adjustments. But then it didn't seem like the uncertainties did grow in the most recent IPCC. Do you have any information about this?
Right, for some reason I've lost my screen share. Hang on, let's, actually I don't think I need to show it, do I? Because I think it is really important. Like, first of all, I'll preface this by saying I am not a climate modeler, so I'm not an authority on this. The information that I gave was mainly me grilling Ben Johnson at the Met Office on how this all worked. So I have to credit him with most of my knowledge on this. But it's important to remember, though, that the error bars are not necessarily just a straight up measurement of uncertainty. You know, you've got to bear in mind how these error bars are generated. So, for instance, a lot of these are generated from multi-model ensembles and so on. So you're kind of exploring these uncertainties. But this will be exploring different aspects of uncertainty and stuff like that. And whilst you can kind of compare the different error bar sizes, I'd be careful not to treat it as an absolute measure of uncertainty. Also, I also have to stress that the values reported by the IPCC AR5 were the instantaneous radiative forcing, and the error bar on that was the error bar associated with that quantity, right? It does not reflect the overall uncertainty on how black carbon is affecting climate. I mean, I think what we should take from this is we've got to be really mindful of what we're actually representing when we quote watts per square meter. It is not simply just a number with an error bar that measures global warming. What we have to do is bear in mind that we are dealing with all these very complex effects. These numbers are produced by models that are getting more and more advanced as the years go on, but it does mean that the conclusions become more and more nuanced. And I'm sure there's lots more surprises that we're waiting to find in the kind of modeling sphere as we go on as well. I think this is, so I wouldn't read too much into comparing uncertainty estimates just
Okay.
as I wouldn't too much into comparing the absolute radiative forcing estimates. You know what I mean?
Okay, I understand. Thank you so much. Accept and appreciate more nuanced views. Thank you.
Yeah. I think we have one question from Dr. Takemura.
Okay, can I ask questions? Hello, James.
Sorry.
Oh, sorry. Okay, you can go first. Go ahead, please.
Okay. So yeah, actually, I have a additional explanation for your James explanation on the rapid adjustment. So actually, may I share screen? So do you see my slide?
Yes.
Yes. Okay. So the as shown as explained in my presentation, so incident radiative forcing by black carbon is compensated by the rapid adjustment due to increasing water vapor shown in CLR by the increasing infrared radiation from the increasing water vapor, and also for the stabilizing the atmosphere due to the absorbing solar radiation by black carbon result in increasing scattering solar radiation by lower cloud, and also the sensible heat, latent heat is also decrease in the atmosphere. So all of the rapid adjustment are compensated by the toward the weakening the stronger black carbon incident radiative forcing. That is the mechanism of the rapid adjustment. Yes.
Yeah. I mean, thank you for that. You explained it much better than I could. As I stress, I'm not a climate modeler. This was only meant to be form part of my introduction. Yeah.
Okay. Thank you.
Okay, can I ask a question? Do I have more? Still have time for the questions?
Yeah, we have time. Yeah.
Okay. Hello, James. Very nice to.
Hi.
I'm pretty much curious about the eddy covariance flux measurements in Delhi and Beijing, and it's quite interesting. And my question is that I would expect very large variations in the concentration of flux, and how you can use the data to improve or validate the mission inventory, or perhaps you try to find the unknown emission sources missing in the inventory. What is your target?
Well, this is the thing. We've got one paper published on this. Also, I've got a student who recently finished a PhD thesis that's published online as well. So we've published Delhi and effectively published that. We've also got a paper published on Beijing. One of the problems that we have is that we're limited by sites. You know, it has to be where we have these structures that are suitable for measuring black carbon. So in the case of Beijing, you know, this is a very nice facility at the IAP in central Beijing, where we're able to make these flux measurements. Well, one of the things, you know, and you're saying, yes, it would be good if we, you know, we're finding these unknown sources of black carbon. What we found there was that with the fluxes we measured in central Beijing were actually quite low. And we could only make the association with traffic there, but the black carbon emissions from traffic in Beijing were generally very low anyway. This we put down to the fact that central Beijing has effectively banned diesel vehicles during the hours of daylight, and they've also cleaned out all of the two-stroke engines as well. So what that meant was that all of these sources of black carbon were coming from outside of our emissions footprint. So we couldn't quantify those because they were from further afield. But what we were able to do was compare this with the then current emissions inventory and then quantify exactly how wrong the inventory was. I think I can get away with saying that because they've since improved the inventory. You know what I mean? Now we did a similar thing in Delhi. That it was slightly different because we were located in a place where we really were not struggling for sources. But again, though, it would appear that we were dominated by traffic, although there did appear to be some other domestic sources. Okay. London, we're still in the process of processing the data right now.
Well, that was very interesting. Did you see any difference in the size of black carbon particle between Delhi and Beijing, or perhaps in?
Oh yeah, yeah. The particles in Delhi were much bigger.
Much bigger.
We think we just be. Sorry.
Oh, sorry. Much bigger. That'll be very interesting.
Well, yeah, but it's not hard to see why though. The emissions fleet in central Beijing is a lot more cleaner, a lot more modern than in the area of, but mind you, I should qualify this by saying the area of Delhi that we did these measurements in, we deliberately went to Old Delhi, which is a much more, we deliberately went there because, you know, that was a much economically poorer area and where there was much dirtier transport sources and all sorts as well. But yeah, the black carbon cores were much larger in Delhi than they were in Beijing.
Okay, thank you very much.
Hi, guys. There's one question online. Can you see the windows of the chat for the chat?
Say again, sorry?
Can you see the window for the online question? The chat.
Right, yeah, sorry. The BC is coated by OC and perhaps some inorganics is. Oh, do you think the EC can affect the chemistry of the coating? So is that as in the elemental carbon could have a role in any heterogeneous chemistry processes? I think that's what it means, if I understand that right. That's an interesting question. Yeah, so reactions with the between the black carbon. Normally, of course, we think of black carbon as being chemically inert. Of course, the black carbon does come with a load of impurities. It can come with metals and so on as well. So in theory, yeah, I suppose that it could play a role in some of these chemical processes. Exactly what though? I mean, that's an interesting question. Yeah, I wouldn't want to commit to an opinion there. It's possible, I suppose. Yeah.
Okay. Second question on site or online? I think we still have time. Oh, this one from Hanaya.
Yeah, thank you very much. Do you hear me?
Yeah, I can hear you.
Okay, thanks. And yeah, I'm interested in your talk a lot. And yeah, I was reviewed for the IPCC-6 for the chapter 6 SSCF. And yeah, I'm involved in the black carbon studies. And yeah, my question is about the lifetime estimation of the black carbon in the atmosphere. So my view on the IPCC-6 is that partly the reduced radiative effect is coming from the reduced lifetime of the black carbon in the atmosphere. And it's yeah, of course, the ensemble mean of the models determine that quantity only. So then, yeah, my question is about what would be the best way from the observational perspective to better constrain the lifetime of the black carbon in the future?
That's a very, very, very good question, because I mean, what we I showed some of our own data that is taken using the BA146, where we're able to look at individual plumes. But this is kind of you're kind of restricted to the number of plumes that you have there, and we're not able to produce any really good statistics on what the typical atmospheric lifetime is, just based on a limited number of plume intercepts. I think the best chance that we have is using the much more extensive data sets using longer range aircraft. and then comparing this with global model treatments. So the thing I've got in mind here is some of the data sets that NOAA have produced, Shuka Schwartz's group specifically, using missions such as HIPPO and the ATOM missions, where they produce these very extensive global observations in situ measurements, and then they're able to constrain this with global models. So they're able to compare this with global models and then test the plume lifetimes using that. I think you'll be able to produce much better statistics using that. I mean, you'll notice what I'm not advocating at the moment is trying to constrain global models using measurements of like the satellite-based observations of AAOD. Personally, I still need to be convinced that the satellite measurements are a good reflection of what is being observed in situ. I'm sure some satellite people will disagree with me when I say that, but you know, that's a separate debate.
Yeah, thank you very much.
Thank you. So I think this section is a time to close. So thanks, Dan. So basically, maybe we have for discussion. Thank you. So let's give the time to Professor or Vice President.
Well, on schedule, we should have 30 minutes for panel discussion. But however, right now it's only 5 minutes left. So I wonder if there's any question or comments. I believe all 3 speakers still online, so they will be happy to answer the question. Or if not, well, I would like to thank you again. Yeah, I noticed there are still around 30 colleagues keeping on the line, and in the room there's also about 20. I appreciate for your journey with us in this motion, and also thanks to our 3 speakers for such excellent talk. Thank you all. Thank you again.
Oh, hi. Hi. Hello. Hello. James, are you there? And the other 2 speakers?
Yeah, I'm still there.
No, I just want to ask all the presenters and also the chair, if possible, can turn on the camera and we can take a picture together for this event, for this special symposium. And I would like to invite Professor Chen to come with the, please stand in front of President Jensen. So, yeah, please. So we can take a picture. Please. Okay.
小心。
好嘞，3、2、1，好，你们站一张，3、2、1。OK， 是。
台湾 style。
Again, on behalf of organizing committee, I would like to thank all your involvement and contribution. I think there is a great discussion and learn. Attendees, both including me, learn now from this special symposium. Thanks.